All right, hello everyone. My name is Gregg. I am an assistant professor in mechanical engineering and bioengineering, and you'll soon see why I'm in both departments. To kind of give you a little bit of background on me, I did all of my formal training in electrical engineering and computer science. And then I spent 3 years working at a hospital to learn about clinical applications, and so I could actually try to make a difference in that field. And so today I'm going to be talking to you about how I hope that walking robots will revolutionize prosthetics, particularly lower limb prosthetics, over the coming decade, and how my research is trying to advance that goal. So just to motivate the talk a little bit, I want to just discuss some of the challenges that are typically faced by lower limb amputees. So we see that this gentleman is a bilateral above knee amputee, meaning he's missing both of his legs above the knee, and so he has two above-knee prosthetic legs, and those are actually state-of-the-art prosthetic legs. But you can tell from the video that he still struggles to walk. It's amazing that he can walk at all, to be honest. But he manages to walk because of the fact that he has canes to maintain his balance, and that he has to use them to make sure he doesn't fall. And so this is fairly typical of some lower limb amputees, in that walking tends to be slower, less stable, and consumes more metabolic energy than that of able-bodied individuals. And so all of these challenges are essentially due to the fact that prosthetic legs nowadays are passive mechanisms. And what I mean by that is that they do not replace the propulsive functions of the muscles in the biological legs. So they can bend and they can respond to the environment, but they can't actually push like your muscles do. And so one way to attempt to address this challenge is to add motors to these legs. And so we've seen that very recently with some research, and also a couple of prosthetic legs that have entered the market, such as the one we see here, where this gentleman has two powered knees, meaning they have motors. The motors can push, and they could also pull. And despite the very advanced hardware, this gentleman still needs to use canes to maintain his balance. And so essentially, the technology is very capable of restoring the lost function of the muscles, but they're very difficult to control. So now imagine this. We've added sensors, we've added motors to these prosthetic legs. So now these devices need to make control decisions hundreds of times, sometimes thousands of times every second. Kind of like some of your very advanced cars nowadays have computers that are constantly making stability, traction control decisions. It's a very similar way that these robotic legs are doing that. And so that presents a very difficult design challenge that we have to tackle as a field. And so fortunately, there could be some solutions to these challenges in the field of walking robots. And so we'll see in this video a very capable, probably the most advanced humanoid robot in the world, which was developed over the past 5 years by Boston Dynamics. So these robots can walk, they can climb stairs, some of them can even run, all on their own, and you can push them. And there have been other videos where they actually kick these things, and they recover in an amazing way, just absolutely amazing capabilities. Now these capabilities have only been developed over the past 5 to 10 years. So it's very recent technology that demonstrates the potential for things like prosthetic legs. So if we can make robots walk like this, why couldn't we make a prosthetic leg walk like this? And so that begs the question of, okay, how do we, given this technology, how do we encode human-like behavior so that it feels like a biological leg to the amputee who's using it? It shouldn't feel machine-like. It should feel very natural. And so that's when we put in our bioengineering hats in my lab, and we look at how able-bodied humans walk. And so we're trying to reverse engineer how we walk every day. And so in the lab, you can see here, this is actually not my lab, but a very similar device in my lab. We have something called a force plate, which measures the forces and the pressures imparted from the body, particularly from the foot against the ground. So this tells us how hard the muscles are pushing and so forth. We also have very special cameras, kind of like what Ryan McMahon was talking about, that can detect these specialized reflective markers that we attach to the leg, and then essentially digitize that information on a computer, which we can then view and analyze. And we're analyzing both both the motion of the leg and also the forces of the leg, so that we can try to understand it and reproduce it on a prosthetic leg. And what's more, we can also do things like perturb or disturb the gait of a human. So imagine a device like we see here, which unexpectedly rotates the ground surface to essentially rotate the ankle. This is what we call a perturbation. It's a disturbance that was not expected, and there's some sort of reflexive response to this disturbance. And so if we understand how humans respond to these types of disturbances, then we can also program those reflexes into a robot, like a prosthetic leg. So once we understand how a human walks, then we need to actually build a robotic leg that can mimic the functions of the biological leg. And so that's when we put on our mechanical engineering hats, and also it also involves a lot of electrical engineering. And so I have to give due credit to some of my collaborators originating from Vanderbilt University. They developed one of the state-of-the-art robotic legs being used for research right now. And so essentially, the components that go into a robotic leg include sensors at the joints to measure the joint angles and velocities. We have motors to move the joints. So the motors create forces, torques, to move the joints. And then, of course, we need a battery and then some power electronics to drive those motors. We also have the transmissions, kind of like gears. You have gears in your car, right, which help at different speeds where you have different torque demands. We also have gear or transmissions in these devices as well to amplify the torques. And perhaps most importantly, from my perspective, is the computation. And that's where we have a microcontroller, which essentially is like a little miniature computer that you're wearing. And it's super lightweight, super low power requirements. And you program all the intelligence into that device. And so we heard someone talk about software engineering earlier, and that's a lot of software engineering as well as control engineering and so forth. And we also might have sensors in the feet to measure forces against the ground in some cases. And my lab is actively developing hardware that we can test in our, for future experiments as well here at UT Dallas, using very similar principles, building on them. So just to demonstrate that this could actually work, I want to preview some very recent experiments where we recruited above-knee amputee patients. This is conducted in Chicago with some of my collaborators there. And I programmed the robotic leg to walk as kind of like a robot would. And you can see that this patient here is able to walk pretty naturally. He's not using the handrails. He's not using canes. We didn't push him like we push robots often. That wouldn't be very fair at this stage. But what you can see, though, is that he's able to maintain a natural-looking gait. It has this nice heel-to-toe motion that's very indicative of natural walking. And we're able to even change the walking speed of the treadmill. We tell the subject, but we don't tell the leg that. The leg just measures it and then adapts using these robotic technologies that have been innovated over the past 10 years. And this is a walking speed that's quite fast for most lower limb amputees, or at least above knee amputees. And so now that we've demonstrated that this can work and produce natural walking, the goal that my lab is currently investigating is trying to produce different locomotor tasks that we use in everyday life. So walking up ramps, stairs, and even running. And running is kind of an interesting example because there are prosthetic feet that are really good at running. You've probably seen them in the Olympics last summer Olympics, Oscar Pistorius, shaped like this. They're called blades. And they're great at storing energy and returning energy. But what they're not great at is walking or standing still because they're curved. So if you watch the Paralympians on the sidelines, they typically have to do this, step back and forth, because they're not statically stable because of the fact that the feet are curved. So they're not good for walking, and they're not good for standing still, but they're great at running. On the other hand, the passive prosthetic legs that you typically use at home or walking out in the community they're not good for running. So right now, you can't have the best of both worlds. So what I'm trying to do is I'm trying to develop technology that can execute all of these tasks very seamlessly, very naturally, so that someone could catch the bus, run to catch the bus, because they're late to class and they don't want to walk and miss that bus. So this is I think, a really exciting goal that we're getting close to reaching. And so this is my lab, the Locomotor Control Systems Laboratory. Our mission, just in summary, is to develop and translate robotics technologies and control technologies into high-performance prosthetic and orthotic devices to enable mobility in individuals with physical impairments or neurological impairments. And so I focus mainly on amputees today, but these technologies could also be used in exoskeletons to help people after stroke or spinal cord injury, to help them regain mobility and independence. And so all the topics that I've discussed are very interdisciplinary. So the students you see here, these are my graduate students who are doing very good work in the lab. They bring expertise from different areas, including robotics, controls, biomedical engineering, electrical engineering, mechanical engineering, even software engineering. And they're all experts in at least one of these things. And so if I was to give you advice, in terms of motivating you for your future careers, I would say get really good at least one thing. And then you can do that one thing really well, even in interdisciplinary laboratories like this. And you can really make a difference, even when the problem seems really big and requires a lot of different sets of expertise. Everyone has to be good at something. And then we can all work together to achieve this grand challenge. So with that, I want to thank you for your time and also acknowledge my funding sources, the National Institutes of Health and the Bros Welcome Fund. And I'm happy to answer your questions. Yeah?
Are there any current prosthetics that integrate organic components?
Do you mean like information or
like actual
hardware?
Like humanoid, like flesh, organic components?
No, not really. Well, I could be wrong. I shouldn't say that definitively because there's research, right? And there's always research on something. But I would say that the closest thing we have to human hardware in these prosthetic devices is something called these little muscle actuators that essentially expand and contract like muscles do. So they're mimicking muscle behavior, but they're not real muscles though. It'd be hard to sustain cellular life in a prosthetic leg without some sort of, maybe I'm not answering your question though.
No, you are.
Okay, great. Yeah.
How far away you are from having a limb that you would want to switch it out from having a real leg? Like,
meaning someone who would opt out of having a biological leg?
like better than you want. Like they like the FIFA team that they can beat the
Yeah.
FIFA team.
So I think we're really far from that. I think 20 years at least. So there's this whole debate for the Olympics with Oscar Pistorius as to whether he had an advantage over the able-bodied Olympic runners. And there was even a whole trial about it. And eventually, the first time he tried, he was not allowed to compete in the Olympics because of his prosthetic legs. And the second time, he was allowed to compete in the Olympics. And I think in his case, he has essentially a spring for a foot. He's missing the ankle. And so the spring is really good at storing energy and releasing energy, but it can't create its own energy like the muscles do. So he has to spend all this time and effort accelerating up to speed using his knees and his hips to compensate for the lack of ankle. And then once he gets there, he's pretty fast. But I would not say he has an advantage by any means. Now, as we add motors and so forth, I could imagine that happening, that you could have motors that are stronger and maybe lighter than muscles in terms of their power density, but the actuator technologies or the motor technologies are not there yet. So until the motors get small and powerful enough, I don't think we're going to see more capabilities than human. Yeah?
How about something that looks like skin on the leg, like flubber, like Answer Robotics has with the legs?
Yeah, so there's something called cosmesis. So typically you'd have some sort of rubber shell either over the prosthetic foot or sometimes over the leg, but rarely it's over the leg because there's a lot of moving parts. But typically what lower limb amputees will do is they'll just wear jeans, just pants, and you never know the difference. But yeah, there are things like cosmeses, which are rubber or some sort of silicone material that, and Walter could probably tell you more about what's out there in terms of the material properties. And they're meant to look somewhat flesh-like, But some people actually like the look of the bionics. You know, it looks flashy and cool, and some people like that. So, yeah.
Most of the models that you know showed up there either have a battery pack or they're plugged into a wall outlet or something for power.
Yeah.
Is there anything either in place under development so that you can recover some of the energy back in the flex of the knee or the spring of the heel to extend your operating time?
Yes, so on the material side of things, having some flexible materials which allow you to, allow the material to bend, which in effect stores energy and then eventually releases that energy, that's really important from the hardware design perspective. So the feet that we have, and also sometimes you can even fit springs in series with a motor, and that helps too. In terms of on the electrical, the power electronic side of things, there certainly is research trying to be able to regenerate power when the motors are doing negative work instead of positive work. There's no such thing as a perfect regeneration, but kind of like your hybrid car or whatnot, when you're braking, you should be able to regenerate some of that power, and there is research doing that. But the challenge, of course, is having something that's not too complex to build and sell. Yeah, but that's great though, because you want to be able to walk all day long, and these devices are pretty good at that already. We can get a day's worth of walking at them. Now, if you're trying to climb the Sears Tower, you might need to switch a few batteries, which has been done, by the way. Any other questions? Yeah.
The video sample that you showed of the gentleman walking on the treadmill,
Yeah.
that Vanderbilt money, how heavy is it? Because he makes that first motion to pick it up. Is it pretty heavy or is it not?
It's less than 10 pounds. Yeah, which is heavier than 10 pounds, but it doesn't feel light to the patient though, because think about this: our legs are attached to our skeleton, and whereas with the lower limb amputee, it's attached to soft tissues at the stump, and so it's actually pulling and tugging on soft tissues rather than the actual skeleton underneath, the bone underneath. So it actually it feels heavier. Yeah, so the goal is to make it as light as possible. There's so many amazing constraints, which is frustrating at times, but it makes it a really interesting problem to solve. Yeah. Any other questions?
What kind of degree would you, if you wanted to be involved in this prosthetic design, what kind of a degree would you have as an undergraduate, for example?
And any of these, for example, there's also people that go to prosthetic school. You can get a degree in prosthetics orthotics. You'll be learning how to fit prostheses that are currently available on the market. And some people do research from that background as well. But really, you can't go wrong. You really can't go wrong. Any discipline of engineering, material science, computer science, anything can be used because this is so translational, so interdisciplinary. Yeah.
I know it lists computer science up there.
I ran out of. But we have to program these things. We have to make sure that the algorithms are safe. One thing we can't afford is to have people fall, especially if you're talking about exoskeletons for, say, geriatric patients. You can't risk a fall because that could break hips and so forth. And so it's a safety critical application, and computer science is actually a really important field for bringing these things to market. Absolutely.
One more question.
So my answer to Ann's question would be a UTD degree.
Yes. Yes. If I wasn't clear about that, I had to give credit to my collaborators. But if you want to do all these things and do it all in a lab like this, you should do it here.
Thank you.
All right. Thanks very much.